continuous learning from Vedantu.
The last one, I was speaking to you about this. H2, Cl2, Br2, I2. This is a gas, this is a gas, this is a liquid, this is a solid. All are nonpolar. What kind of forces are present in these elements or in between these molecules? Hydrogen, and there is force of attraction, we know, because we can liquefy them. This is already in the liquid state. This one is in the solid state. So what is the force of attraction there? We will see. That is actually done by Fritz London. That is the reason it is called as London dispersion forces. Dispersion forces. It is dispersed throughout the substance. And the magnitude is so high that it is able to bring the molecules closer. Non-polar molecules cannot exist as solid and liquid. They should be only gases. This was the, understanding before. But however, the examples which I told you, benzene is a liquid. This is a non-polar molecule. And CCl4, okay, that is also a liquid. Non-polar substances exist as liquids means there must be intermolecular forces of attraction. Okay, that is, there must be stronger intermolecular forces of attraction, I would say, because it is in the liquid state. So what exactly happens here is a non-polar molecule having zero dipole moment. No, it is not. It is not corrosive. Okay, it is a volatile liquid. The moment when it comes in contact with it, when you put it outside, it starts vaporizing very easily. Boiling point is very less. Okay. So in your labs it will be there, benzene. Okay. It is used as a solvent for non-polar molecules. So in non-polar molecules, no, you don't use it actually. For 11th and 12th, there is no experiment except that we do the activity of like dissolves like. That's it. For that we use. Otherwise, there is no experiment. Immiscible liquids. Earlier it used to be there. In solution, there is a chapter in 12th. Miscible and immiscible liquids. Now it is not there. Earlier it used to be there. So there we used to do some activity using benzene. Okay. Yes. Now coming to dipole and induced, London dispersion forces existing purely in nonpolar molecules. Okay. Now you see, if the molecule is nonpolar, we expect the electron density to be symmetric. Am I right? Spherically symmetrical. Like this. Okay. But the electrons are not stationary. Am I right? They will be moving all the time. And because they are moving, sometimes, maybe a fraction of a second, more electron density, more electrons will come to one side of the molecule. That is possible, isn't it? There is every chance that more electrons will come to one end of the molecule, one side of the molecule. So therefore, at that moment, that end of the molecule will get slightly negative sign because more electrons were there. What about the other end? That will be slightly positive. Now this polarity which is there, which has come to this molecule, start inducing polarity in the neighboring molecules. If this is positive, this will be negative because it will attract the electrons towards itself. Okay? So therefore, when it starts attracting that, there will be, induced polarity in the neighboring molecule. So because of this, a non-polar molecule having zero dipole moment is shown here. This is what happens. See, I was telling this negative end of the molecule, if it is there, it will start inducing the opposite charge, the neighboring molecule. So because this end is positive, the other end, the more electrons will be more on the other side. Okay, like this continues, dispersed. And the molecule, between the molecules where it starts may not be there, but it will have already induced the dipole in various other molecules. That is the reason it is called as dispersion forces. It is dispersed. It is everywhere. London dispersion forces. Instantaneous dipole moment. At that instant of time it will be there. It will not be there in the next moment. Okay? So by that time it will have already induced dipole in other molecules. Okay? So this is London dispersion forces. The basic reason why it exists is electrons are not stationary. They will be moving all the time. When they are moving, there is a moment when they come, more electrons come to one end of the molecule. That is possible, isn't it? So that is the reason this one. So the magnitude could be so high that in case of iodine, I2, even though it is a non-polar molecule, it comes to solid state. See how strong. Actually, the magnitude of this London dispersion forces increases with increase in. This concept explains as to why nonpolar molecules could be in liquid and solid state as well. Okay, gaseous state. Because polar molecules, it is very easy for us to understand, isn't it? There is force of attraction between the molecules. They can come closer. But what about nonpolar molecules? They also exist in liquid and solid state, but they don't have any polarity. What kind of force of attraction should be there? What kind of interaction is there? Isn't it? There has to be some force of attraction, isn't it? Which is keeping the molecules together. And that force of attraction is London dispersion forces, which exists because of the instantaneous dipole moments which exist at that instant of time. Okay? Now supposing a question is asked, explain why iodine, despite the fact that it is a non-polar molecule, exists in solid state. If this question is asked, what is your answer? What kind of force of attraction is there? There has to be some force of attraction, otherwise it cannot be in the solid state. How do you explain that? Yes, correct. London dispersion forces, which exist because of instantaneous dipole moment. Okay, this kind of questions can be asked. Charge fluctuation, correct. Right? Like that. Very interesting, this particular one. We think that it is very weak, but its magnitude depends upon the number of electrons. If the number of electrons is more in the molecule, more is the magnitude of dispersion force. Okay? Like iodine. Lot of electrons are there. 120, I don't know how many electrons there. I don't remember its atomic number. Those many electrons will be there. 88, suppose. Let me tell you that. 53. 53 electrons in one iodine atom. 53 plus 53. Those many electrons will be there in iodine molecule. Okay, how many electrons? See, therefore, the magnitude is also very high. Okay? This is fine? Oh, very nice. That is good. In fact, I too had it, but somebody took it from me. Oh, very nice, very nice. That is actually a good practice. So next time, whenever I want any atomic number, atomic mass, I'll ask you, Manav. It is right in front of you. Good, good. That is a good practice. Yeah. Oh, very nice. Very nice. So I have a small one. I have to wear my specs to see that. Right? Okay. Devi Prasad, any doubt? London dispersion forces, very, very important one. Okay. See, in fact, you could have asked me, I was expecting one question from you people. What is that question? London dispersion forces could be present in any molecule, polar, non-polar, whatever. Because see the very existence. Okay. But the thing is, this is the weakest force of attraction. First one is ion dipole. Strongest. Then comes dipole-dipole. Next is dipole-induced dipole. Okay? The last one is London dispersion forces. This is present. But then the magnitude is very, very low compared to these forces. That is the reason we don't consider. When we consider other molecules, it could be there. But magnitude is very, very less. It is like having, say, 1 kg of rice and few grains are there outside. We don't even bother, isn't it? Because this is, compared to this quantity, this is very, very less. But it is there. Right? Same thing with this also. Because the magnitude is very less, there is no need to add this kind of forces to the other stronger forces. Right? Okay. This they have explained. See, this is how actually happens. Due to constant motion of electrons, an atom or molecule develops a temporary dipole. This is, all these are van der Waals forces. Okay? All these are considered as van der Waals forces. Even ion dipole is not included. It is dipole-dipole, dipole-induced dipole, and London dispersion forces. All are van der Waals. The force of attraction which are present between the molecules. Okay, which are not bonded directly. They all come under van der Waals force of attraction. Okay? Of course, yes, correct. That is true. Different types of van der Waals force of attraction. This is the cause of development of temporary dipole on the non-polar molecule. Okay, this is the cause. So because of this, the second atom, the neighboring atom in turn gets distorted, which leads to an electrostatic force of attraction between the two atoms. This is what is London force of attraction. Okay, so this is the definition for London dispersion forces. It is attraction between two temporary dipoles of an atom or nonpolar molecules. Okay. Yes. Devi Prasad, you're back. Right. Now this is what type of intermolecular force of attraction water has. Okay. What type of intermolecular forces here? Water, if you take whether it is C here, this is what I was speaking to you. All molecules will have this dipole-dipole interaction, and a special type we call it as hydrogen bonding. So this is always present. This is present everywhere in all the molecules. Now see here, there is an example here. Water is dipole and there is force of attraction, and this is the molecule formed by oxygen, nitrogen and fluorine. Okay, and what is the strength of this? Dipole moment is 18 dB in this case. 18 dB is 18 into 10 to the power minus 30 coulomb meter. Okay, some unit is there, so it is 10 to the power minus 30 coulomb meter is taken as dB. That's all. Okay, so which is the magnitude of charge in coulombs and distance of separation, that is the length, which is in Armstrong, are converted into meters. That's it. Strength of this bond is the same. Both of them are equally polar. That is the meaning of that. Okay, mu, dipole moment, will tell you only to what extent it is polar. Okay, polarity of a molecule is measured in terms of dipole moment. That's all. Higher the value of dipole moment, more is the polarity. That's it. Both of them are equally polar. That is also same. But the thing is, boiling point. Boiling point is the one which tells you, is a measure of the strength of the intermolecular forces. Higher the boiling point, higher is the stronger is the intermolecular force. Okay, so water has got very high boiling point, 100 degrees centigrade. Ammonia has got much lower. I don't remember the value, but then it is much less than 100 degrees. Both of them have got hydrogen bonding, but still the strength of hydrogen bonding is more in water than in ammonia, because the electronegativity difference between NH and OH, this is more, this is less. Okay, so that means boiling point is a measure of the strength of intermolecular forces present between the molecules of that sample. Now in this case, it is a very interesting case. See here, both being polar, having the same strength for polarity. See the boiling point. Boiling point is 100 degrees centigrade. Boiling point is minus 56. If this is formed, ONF. What is the reason? The reason is these are all electronegative elements. Oxygen is the second most electronegative element. Fluorine is the first one. Okay. So in this case, what happens is the bond formed between hydrogen of one molecule and electronegative atom of the another molecule, we call it as hydrogen bonding. This kind of hydrogen bonding is not present here because hydrogen itself is not here. Correct. It will be only dipole-dipole interaction. So we know that this bonding is stronger than dipole-dipole interaction. Okay, these kind of questions can be asked. Hope you followed this. I will show you once again. See here, the strength of the bond is the same because both of them have same dipole moment. In spite of that, water has very high boiling point, whereas this molecule has got lower boiling point. What is the reason? The reason being, we find hydrogen bonding in water, but we don't find hydrogen bonding here. We are supposed to be seeing the force of attraction between the molecules, isn't it? It is much, much weaker. It is only dipole-dipole interaction because of the weak polarity of the molecule. These are three electronegative elements. So we won't find much difference in electronegativity of these three elements. Therefore, it is only a weak, ordinary type of dipole-dipole interaction we see. This is dipole-dipole interaction, that is hydrogen bonding. Hydrogen bond is very strong. Hence the difference in boiling point between these two is 156 degree centigrade. It's a very interesting one. Okay, followed this one. Yes or no? Yes, okay. Manav? It is strong because of equally strong magnitude of charge. That's it. Even though it is like this, one end of the molecule will be slightly negative, fluorine end. These two are there. And this end of the molecule will be slightly positive. Okay, because of that, and the length of the bond, it depends on both. Okay, length is more. Charge, even if it is less, length is also comes, no, with the dipole moment. Mu is equal to Q into length. Both put together, you will get the same value. That's it. Okay. It is not one quantity. It doesn't depend only on charge. It depends upon the bond length as well. Okay? Yeah. So that is the one, right? And hydrogen bonding is this one. In hydrogen bonding in HF we see, because of which it is in the liquid state. This is hydrogen bonding in water molecule. This is how we are supposed to, not shown here, like this. You have to show. Water molecule. Oh, it is shown here. This is in ammonia. Hydrogen bonding in ammonia. Because of which it is in the liquid state. Next.
So ma'am, in these cases we have to compare more than one factors, not only the dipole moment.
Yeah.
That's why.
Yeah, true. What kind of force is present between them, that you have to see. Even though it is dipole-dipole interaction, there is a difference. Okay? Those questions can be asked in competitive examination, depending upon intermolecular forces especially. Okay, they might ask you, say for example, when ammonia is given, water is given, NHF is given, NHO is given, which of these has got the highest boiling point or lowest boiling point? Okay, in that case you will have to, say for example, if these four are given, H2O, HF, and then NH3, and then NHF is given, NOF is given. Which of these has got the lowest boiling point? Student will not think, because they will not have come across this molecule at all. They will forget that all these have got hydrogen bonded to an electronegative element. In any case, the boiling point of these three should be higher. Okay, this is not having hydrogen but only the electronegative elements. This can be polar. That is the reason it will have dipole-dipole interaction and hence lowest boiling point. Like this you will have to think. Okay, these three will have higher boiling. Among these three, if you take, this one will have the highest boiling point. Then comes this. Then comes this. Okay, like that. So logically you have to think. If you know the concept, then it is easy for you to think. Then this is another point. We spoke about intermolecular forces of attraction. This intermolecular force of attraction brings the molecules closer, whereas thermal energy, if you heat, then the molecules tend to move away because of increased kinetic energy. Okay, so these two act in in opposite directions. Increase in intermolecular forces brings the molecules closer, whereas increase in thermal energy separates the molecule, separates the particles. Okay, using this fact, we use thermal energy to interconvert different physical states of matter. If you heat a solid, it is going to be liquid. Liquid further heating becomes a gas. And on cooling, gaseous substance comes to the liquid state and so on. Okay, that is the fact. So three states of matter are the result of balance between the intermolecular forces and thermal energy of the molecule. There has to be a balance. Otherwise, one will take over the other because they are acting in opposite directions. Okay, there has to be a balance between these two. A simple point. Now let us move on to a gas which we don't know whether it is going to exist or not. If at all it exists, a gas exists like this. Gas molecules are there. And they will be moving all the time. If this happens, then what are the characteristics of this gas which we consider as ideal gas? Okay, what is that actually? Say for example, in Bangalore, if you consider we want an ideal road, what comes to your mind? It should be big, it should be wide, no potholes, no paper pieces, spread here and there, no dirty things. All these things comes to our mind. That is the ideal road for us. Okay, so that is in a similar way, we imagine an ideal gas, how it should be. If an ideal gas exists, then the intermolecular distance are very large. Hence, intermolecular forces of attraction, that is, intermolecular forces are negligible. They are far apart. There is no interaction. There is no force of attraction. Okay, that is what the first one. Second one is, the volume occupied by the molecules is negligible in compared to the volume of the container. For example, for a moment, if you think that all the molecules are condensed to one small area, then this will occupy only this much space. All the molecules put together, only this much. Rest of the almost 99% of this container is empty. What is the meaning of that? The volume occupied by the molecules is negligible in comparison to the volume of the container. Okay, hardly any volume these gas particles are going to occupy. This is the second characteristic of an ideal imaginary gas. Third one is, the molecules of the gas are in continuous random motion. That we can see. It is true for any gas molecule and it is true for an ideal gas as well. They will be in a state of constant motion, random motion. They can move in any direction. And when they are moving, there is every possibility that they are going to collide with each other. Okay? And they collide and still they are moving in constant motion. That means what? During collision, there is no loss of kinetic energy. If there is no loss of kinetic energy, we call that collision as elastic collision. No loss of kinetic energy. They collide and they move. Okay, and the laws of classical mechanics is applicable on the molecular motion of the gas. The meaning is Newton's laws of classical mechanics. You will study this in physics. That is, law of conservation of momentum and all those things you will study. They are all applicable here also. For just like any moving particle, here also they are applicable. These are the things which comes to our mind when we think of an ideal gas. Whether there is an ideal gas or not, we are yet to see. Okay, we will see soon whether it is there or not. Okay, so those are the assumptions of an ideal gas. Now we want to, in order to study those things about a gas supposedly called as ideal gas, we need these parameters. What is that? We need to know the pressure of the gas. We need to know the volume it occupies. We need to know the temperature. We need to know the number of molecules, that is moles. Okay? These are the 4 parameters which describe a gas mole, which are those: pressure, volume, temperature and number of moles. Using this, we can describe a gas and its state. Okay? These are called as state variables. Now supposing, what is the meaning of that? State variables means, say for example, you have got a gas STP at STP. A gas I have taken, I maintained it at STP. 1 mole of gas, oxygen gas I have taken. Okay, put it in this container, there is a piston. And this is 1 mole of oxygen. Okay, O2 at STP. What is the volume? 22.4 liters. Now STP means 0 degree, 273 Kelvin. Now I will make it 270 Kelvin. I will reduce the temperature, I will cool it. Then do you think the volume remains the same? I have changed the temperature. Pressure remains the same because the pressure acting on this is the same. Number of moles I haven't changed. But because I have changed the temperature, volume would change. Okay, volume now it will be lesser. It comes down. That is the meaning of that. Not necessary that all the state variables change at the same time. There is no need for them to change. We can keep 1 or 2 constant, and here I have kept the pressure constant, number of moles of the gas constant, and the other 2 change. It is like that. So like this, these variables we keep changing to study the characteristics, the properties of these gases. So in order to do that, we need these 4 variables. They are called as state variables. They are going to change the state of the gas from one state to the other. That's it. Okay, so this state variables which we will learn is this: pressure, volume, temperature, number of moles. Now before we do that, we should know how to measure pressure, isn't it? What are the different ways of measuring pressure? What are the different units? Same thing for volume, temperature, number of moles, of course we know. It is with respect to the Avogadro. Yes, force per unit area, very true. And all this. This is important. Let us take it up first. STP and NTP. So STP is 1 atmospheric pressure and NTP generally is taken for 1 bar pressure. That's it. There is a small difference between atmosphere and bar. That's all. Otherwise no difference. Even if you can take it as this, the value, hardly any change in the value because there is very small difference between these two. Right? Or it could be the other way around. It may be this, the STP is bar, or this is atmosphere, like that. Okay? Small difference is there. That's it. But we use interchangeably. Many books, many questions you must have seen. Okay? Interchangeably we use because there is hardly any difference between the numerical value of these two. So we will see that now. Okay? Right. Move ahead. Yes or no? Yes. Okay. Let us try to understand volume. How will you measure the volume of a gas? Volume of a gas is measured in terms of liter, in terms of decimeter cube cubic decimeter, centimeter cube, meter cube. So even though the SI unit of volume is meter cube, we still use liter, centimeter cube. These are all smaller units. This is a very big unit. This much volume in under normal conditions, in the laboratory conditions, we can't use because it is too high. So we use all this, decimeter. Even in competitive examinations, these are used still. Okay? So you need to understand the interconversions of these. Okay? 1 liter is equal to 1000 ml, which is same as 1000 centimeter cube, which is equal to 1 decimeter cube. That is 1 liter is equal to 1 decimeter cube. Okay? If you forget for some reason, you can derive it. Don't have to worry. It will take hardly any time. Only one relation you should know. That is, this one. I had a student who was too good. Okay, but these interconversions he used to forget. So we started telling him all this. You don't try to, remember them like that. You just remember the relations. It will take hardly any time to convert them. Say for example, 100 centimeter is equal to 1 meter. If you remember this, you can derive all of them. Okay? So cube on both the sides. Whole cube is equal to 1 meter cube. So you will get 10 to the power 6 centimeter cube is equal to 1 meter cube. This is one relation. Second one is, this is, you can remember, 1000 centimeter cube is equal to 1 liter. Now I can write this as 1000 into 10 to the power 3. In 10 to the power 6 I can write it this way. Centimeter cube is equal to 1 meter cube. Isn't it? So 1000 centimeter cube is 1 liter. So therefore, let me write it here. So I can write this as 10 to the power 3 liter is equal to 1 meter cube. So big it is. Or 1 liter is equal to 10 to the power minus 3 meter cube. Okay, all these have come. Now this one, if you want, 10 centimeter is equal to 1 decimeter. 1 dm. Right. 10 to the power cube on the both sides. Whole cube is equal to 1 dm cube. Okay, this is 10 to the 1000 centimeter cube you will get. 1 decimeter cube. Therefore, 1 liter is equal to 1 dm cube. This is what. Okay? Same as centimeter, correct. Cubic centimeter, cc. Cc or cubic centimeter, both are same. Yes. Move ahead. Right. Temperature. How to measure temperature? We have 3 scales: degree centigrade, Fahrenheit, and then Kelvin scale. So we often use Kelvin scale in chemistry, even though sometimes we may have to convert different temperatures into other scales. Kelvin temperature is very simple. If you want to convert into Kelvin scale, you just have to add T degrees to 273.15, because this is a 0 in the Kelvin scale.
Ma'am, is it 9/5?
Yes, it is 9/5, correct. It is 9/5. Do you know how you get 9/5? Probably you have studied this in your this thing. 9/5. How do you get?
I don't remember.
I will tell you. I will tell you this. Okay, you go through that, And in the next class I will tell you. I will tell you the hint as to how you should do it. Okay? It is there in your NCERT book. If you have the NCERT book, the 3 temperature scales are there in one of the pages. Okay? So you observe the 0 of the Celsius scale and the 0 of Fahrenheit scale. That is the freezing point. And you observe the boiling point. Just find out how many divisions are there in these two. In one you will find 100, in the other you will find 180. 180 divided by 100. You will get 9/5. Correct? And the 0 of the Fahrenheit scale starts at 32. So you add 32 to that, plus 32. You will get the temperature at for this one. This is how you do it. You observe this and you try to do it. You will get this. Okay, and when you get this, you will not forget this. I have seen many students, even though they are very good, this relation they won't be able to remember. Sometimes they will put 5/9. Sometimes they will put this and this interchanged and all those things. So those things you can avoid by looking closely into this temperature scales and then deriving this equation all by yourself. Then you will remember that, okay? Right? Devi Prasad, you also try this. The 3 temperature. Otherwise you can download it from the net. The same image is put in net also. Okay, do it. It will be very interesting. How do you get this equation? Just let me know. This, of course, we are going to derive when we are going to do Charles' law. This we will derive. Okay. So tell Kelvin scale, it is simple. Supposing I want to convert. They have added more. Now I have put 70 pages today. Okay, they have added more. Maybe you people must have told them. Right? Which is good now. In fact, very comfortable. Yeah, I can save a lot of time in rubbing and all those things. Erasing. Okay. Right.